When people say this terrible thing which is not true, which is that we know more about the moon than we do about the deep ocean, categorically not true. Not true.
I've heard that a lot.
Complete nonsense, right? It's nonsense, and it's damaging nonsense. The ocean is a much richer environment. It's much more interesting. And every time people say, oh, well, we know more about the moon than we do about the deep ocean, they make the deep ocean sound like the moon. They make it sound like a dead, barren rock. And it isn't.
Have you ever seen the blue marble photo from 1972? It's that famous image from NASA that shows Earth from space.
And what's really striking about it is the fact that it's mostly blue. But we're so focused on land, the trees,
The ice?
the weather.
We are British after all.
What else would we talk about?
And yet the ocean is massive. It occupies more of our planet than land, and it's massively important for our survival too.
And so in the climate question from the BBC World Service, we're asking, what does the ocean do for us? I'm Jordan Dunbar.
And I'm Greya Jackson. Helen Czerski is all things ocean. She's an oceanographer and a physicist at University College London in the UK, and she's also written a book called The Blue Machine: How the Ocean Shapes Our World. Hello, Helen.
Hello, it's lovely to be here.
Helen, one of my guilty pleasures is spending hours watching videos of huge storms and heavy seas. And I'm not alone, there's quite a lot of us out there watching massive waves crashing into lighthouses, ships bobbing up and down. But it's mostly because I'm not there, I'm on my sofa. But you spent a lot of your time actually in those ships, haven't you? You've been there. Tell me about some of the biggest waves and the storms that you've had to go through in your career.
That's a niche occupation you've got, I have to
Thank
say.
you.
Clearly you're in good company. So most of the biggest waves are not at the coastline. They're out in the open ocean. And one of the things that I, as someone who studies breaking waves, one of the things that I find myself having to explain again and again is that the ones at the shoreline are not the ones that matter for the ocean. They obviously matter for humans. They matter if you're standing on the beach and there's big waves coming. But actually, that's not where most of the wave energy is. If you think about the edges of the coastlines, that's a tiny, tiny fraction of the whole ocean. Where most waves, breaking waves in the ocean are out in the open ocean, where, of course, there's no obstacles, so wind can blow very quickly. You get big storms that build up, and that can make the waves huge. And, of course, once you've created waves, the weather has put all that energy into the waves don't just go away, they travel. And so though the swell, and that's what swell is, can just move away from the storm for enormous distances, thousands of kilometres. And the problem is that I'm interested in the top metre of the ocean, and that can be going up and down by 10 or 12 metres. So getting in there, into that physics, can be quite tricky. But basically the only way to do it is to get out there, to take a big research ship, to sit on the ship, and then to basically chuck your experiments over the side and leave them to float off in this massive storm while you sit on the ship and hope they don't sink, because there's nothing you can do about
And
it.
hope you're not sick in the process. Some of the waves must be massive.
Yeah, what's it like being on those waves?
The most dramatic waves I've ever been at sea on were probably in 2012-ish and 2013. And what was nice about that situation, if you like, was that the swell was coming directly towards the ship. So the wind was blowing this way. It had been blowing across the ocean for hundreds of miles. So there was a huge swell, and then the wind was blowing this way. So the ship was sitting bow into the wind, and you're just riding up. You're just facing into it, riding over the top. And that is a very dramatic place to be, especially on a big ship, because you can see there's a sort of delay, right? You can see the ship is going to plunge down into the waves, and you wait, and then the splash comes over the bow.
Like a roller coaster?
Yeah, a bit like it is like a roller coaster. It's less pleasant when you get swells and winds coming from different directions. And then there's this kind of, it doesn't look quite as dramatic, but it's very violent because everything is coming from everywhere. And in practice on the ship, I mean, for my colleagues, they've got to try and work in those conditions. I have normally put the kit over the side, and I'm just checking that it's still sending me its location.
You're just videoing it?
Well,
sending it to people
so
like me?
it's disappeared. It's probably kilometres away at this point. They float off in the wind quite
Are
quickly.
you doing that lying down?
No, well, I don't mind I quite like the waves. I quite like being rocked to sleep as long as I'm not being chucked out of bed. Ship beds on ships do have straps actually, so you can strap yourself in. The worst bit is hearing the sliding, because you wake up at 3 a.m. and you hear something sliding. You think, oh my God, my lab's just down below or up above or wherever it is. Maybe that's my kit. Maybe that's my equipment that's sliding around. So you get up and go and have a look. So I'm continually getting up in the really big storms at 3 a.m. and just going, is it still all okay? If you smash all your kit on the first day, you have a real problem, right? There's no one's coming to save you, right? There is no replacement. There's no B&Q down the road. So you're done. So there is, I mean, we're all used to it, but when I describe it to somebody else, it does sound like there's a lot of drama.
Not ideal conditions.
But these are the interesting ones. Right? So one of the things that we think about our world is that it is controllable. We're sort of getting this idea that because there are computer models and because there are swanky graphics and because we have satellite images of the whole planet, that somehow we know all the important things. But the thing is that nature is much more challenging and interesting than we give it credit for. And the only way to study that is to get out into it and to face up, to be humbled by the complexity of what's going on around you. And they're all, especially one of the things I think now, there's a lot of very swanky computer modeling going on, brilliant, but it's a model, it's not reality. And it's very easy to be seduced by computer models because they kind of smooth out all the bumps and they make everything look like you understand it. But unless you are very carefully checking that against reality, you're in danger of missing some really big things. Science needs to be confronted by reality. And in a world where computer models get more and more sophisticated, sometimes that's becoming a bit harder. So the reason we need to do this science is because it's difficult. It does make a difference, but it's exactly the bit that kind of gets smoothed over in models because we don't know really how it works because it's difficult. So you've got to go and do it.
It's like the granularity of it as well, I imagine. I mean, in your book, you call the ocean a blue machine. Why is that?
Because it's doing things. The subtitle for the UK version was How the Ocean Shapes the World, but for the American version, it's How the Ocean Works. And a lot of people's first reaction was, I didn't know the ocean worked. And that's because our view of the ocean is that it's this sort of blue filler, it's like the colouring in between the interesting bits which are on land. That's how our maps were drawn when we were kids, and people had maps of, well, you just colour it in blue, right? Get over that, get to the other side. And actually that is missing the entire point of the planet. The ocean is important not just because it's there and not just because it's full of water and not just because it covers 70% of the planet, but because it's doing things, it's moving, it's constantly circulating horizontally and vertically, and it's moving things around, it's moving heat around and nutrients around. It's not the same everywhere. And so the way that this engine turns directly dictates what happens on land. Even the most arid desert-like cultures are affected. The way they live is affected by things the ocean did. And perhaps the most obvious example of this is ancient Egypt, right? Tutankhamun, the Great Pyramid, all of this history. And we are taught that this was the reason ancient Egypt had all this luxury, is that it was a desert culture. But once a year they had this inundation where water flooded down the Nile, and it gave them very fertile soils. They could grow lots of food, so they had spare time to make all these pyramids. Nobody ever asked where the water came from, right? So you got water that has evaporated from the Indian Ocean. It's carried up over the Ethiopian highlands. It rains, and that's the start of the Nile. And that rain is carried down. So you've got a pattern over here which is generated by ocean water and by weather that is driven by the ocean. And that's why you've got a bunch of water up here that can then flood downstream that then feeds to. So even though Tutankhamun possibly never saw the ocean in his life, his entire lifestyle was dictated by something the ocean had done. And that is common.
And that's true today for people listening who don't live anywhere near the sea or may not have seen the ocean. It's also impacting their weather.
Absolutely. So, we know here in Northern Europe that our weather, the temperature of the atmosphere is fed by the Gulf Stream, the warm water coming from the Gulf Stream. And so it's bringing heat. Otherwise, we'd be the same temperature as, Canada, that's sort of, New Brunswick or wherever, where it's really cold. Like at this time, I just cycled here, right? And it's fine in London in November. I would be in, sort of parka and snow boots or something on the other side. And the difference is because of the ocean. So yes, almost every environment on Earth is affected by how the ocean is moving and what it's doing and what it's supplying. And the big things it's supplying are water and heat.
And food, presumably, as well.
And food, yes, of course. So some huge proportion of the protein that humans get comes from the ocean one way or another. Although actually quite a lot of it is secondary. We don't actually eat most of the things we pull out of the ocean. We turn a lot of it into things like fish meal and feed it to other animals, and then we eat the other animals. But yes, for lots of communities, the ocean is their direct source of food. So, and of course, life is navigating around the structure of the insides of this engine. It's not just somewhere, Iceland didn't have cod wars because somebody rolled the dice and there was cod, right? Iceland had cod wars because it sits at the confluence of these different currents that are bringing different things. And so just like a city, it's got a bit of everything.
I think people listening will need you to explain what a cod war is, because it sounds like fish with weapons.
No, it isn't. It would have been more exciting if it had been. So these are wars that were fought between Iceland or this was a huge dispute, should we say, between Iceland and Britain over who had the rights to fish the cod.
Because there's so much cod.
So Iceland is a great place for cod fishing, but obviously the ocean has no boundaries. So who gets to go? And so British ships were going, oh, well, we'll pop up there and take some cod. I don't remember the ins and outs of the whole debate. But the point is, the reason Iceland has lots of cod is that it's at this crossroads in the ocean. It's just like a city. All these different things are being brought from different places. You have different types of nutrients. It's all there. So you have loads of life. And that's why Iceland has cod. And then you have the human consequences of that. So it's all but that's because of what's going on in the ocean. It's because of the sort of shape of the ocean engine underneath.
And the ocean, of course, is really important in the context of climate change because it's sort of been acting as a buffer for climate change. Climate change would be much worse if we didn't have the ocean helping us out in a way. In what ways is the ocean helping us?
So there's two big ways, which is that the first way is that climate change is fundamentally a problem of energy accumulation. So you can imagine if you've got a bath and you've got a tap, the faucet, water's coming in, and you've got a plug hole and water's going out. You can imagine Earth like a bath of energy, and energy's coming in from the sun and it's leaving. Actually, it's being radiated away in the infrared. That's the plug hole. And if you add carbon dioxide to the atmosphere, what you do is you bung up the plug hole. So less energy can get out. So the level of water in the bath goes up. So fundamentally, what climate change is about is that the Earth system is accumulating energy.
And Helen, when you're talking about energy, you're fundamentally talking about heat, aren't you?
Yes, almost all of the energy stored on Earth is stored as heat. It moves around some of the time as light and movement energy, kinetic energy, but most of the energy on Earth is manifested as heat. So then you have the question, you've got this huge amount of energy, extra energy, where is it going? And the answer is that more than 90% of it is going into the ocean. Now, the ocean's actually, it's not great for the ocean, but it's a kind of a good place to keep it. It's one of the reasons the ocean's useful, because it takes a lot of energy to heat up the ocean by only a little bit. And so it's kind of a very good reservoir in that sense, that you can put loads of energy into it and it does get hotter, and that matters, but it doesn't get hotter by a lot. So it acts as a buffer. It's protecting us against, because if we had that heat knocking around on land, Earth would be unlivable now already. And the other thing it does is it takes up carbon dioxide. So we're burning fossil fuels, we're emitting more carbon dioxide into the atmosphere than nature would naturally. And then you've got more in the atmosphere. So as I was describing before, the ocean can take up carbon dioxide. So if you've got lots in the atmosphere and not so much in the ocean, it will cross the boundary. And so that concentration gradient overall drives carbon dioxide into the ocean. So the ocean has taken up about a quarter of all the extra carbon dioxide that we have put into the atmosphere. So that means it's taken it out of the atmosphere. So that carbon dioxide can't cause us problems up here by trapping extra energy. But of course, it's not neutral for the ocean. It then has impacts there. So those are the two big things. And then you get onto the consequences of those things. So if you put heat into the ocean, and it's an engine that is driven by heat, you're going to change the way that engine works, right? You're going to heat it up more in some places and others. You might change currents. One of the big things is that the ocean is layered. So because it's heated from above, that top layer warms up, and a warm water is less dense, so it floats on top of everything underneath. And more or less the way the ocean works is that the nutrients tend to be in the deep water, and this is the bit that this top layer is lit by sunlight. So that's all right. But it means if you want to have life, you can't do anything here because the raw materials are down there and the energy is up here.
Need to mix.
So you need to mix it. So the ocean has these ways of mixing nutrients upwards, and that's why we have life. But if you make this top layer warmer, you make it more buoyant and you make the mixing harder. So in principle, you make it harder for ocean ecosystems to live. So it's called stratification because these sort of strata like this. So these are the sorts of things where they're a bit more subtle, but if you add heat into the ocean, you change the patterns, you change how the ocean works. The problem is that our systems depend on the ocean working as it does now. The ocean will be fine, the life in it might not be, but we depend on this engine ticking along as it does now. So if we change the shape of it, we've got a problem. And so the consequence of the carbon dioxide uptake is that you get ocean acidification. So you change the chemistry of the ocean, and that makes it potentially harder for some types of life to live.
So just to sum that up, it creates our weather, it helps us with providing food, it's shaped our civilizations like ancient Egypt, but it's also put the brake on climate change by absorbing 90% of the heat. That is very high, and a quarter of the carbon dioxide that we have in the atmosphere. I mean, it's doing so many things for us, and that's not even talking about the oxygen that it creates.
Well, so the ocean actually, it creates a lot of oxygen, but most of it stays in the ocean. So there's this myth you hear, it drives gas scientists nuts actually, that every other breath we take is generated by the ocean. Not true. It is true that almost half of all photosynthesis happens in the ocean. So almost half of all of the sun's energy that's captured and turns into sugars, that does happen in the ocean, but it tends to stay in the ocean. So what we are breathing is oxygen that has come from trees and plants on land. But the ocean, there's a huge amount of photosynthesis in the ocean that really matters for life in the ocean. So, and the ocean, one of the sort of side problems somewhere down the list is that the level of oxygen in the ocean is going down, partly because of the stratification, which means oxygen stays at the top, partly because the ocean is warming. So it's always going to have, it will tend to give it off rather than take it in. And partly because we're changing where things are living and growing, and they might be sucking up oxygen in places where they didn't used to be. So it's really interesting in a way that when the Apollo missions happened, and human eyes for the first time were far enough away from the planet to really see it. Back in 1972, when the blue marble, that famous picture, was taken, NASA called it the blue marble. It's a blue planet. And yet we haven't really understood yet that we are an ocean world. So once you see us as living in the shadow of the ocean, it sort of changes your worldview a bit. And then we can understand that if we are changing the absolutely dominant feature of the planet by warming it up, by changing currents, whatever that is, that's a huge deal, right? That's not tinkering around the edges. That is potentially a huge change. So I think until we really understand that, we're always going to be sort of nipping at the edges of the problem rather than facing it head on.
We mentioned all of the things that the ocean machine does for us, absolutely vital things. And then you talked about ocean acidification. What is that doing to the machine and the things that live in it? The UN says, I think, nearly 3 billion people rely on fish or the sea for some form of protein. Acidification doesn't sound great.
No. So the first thing is that the ocean is, before we came along, it's a bit alkaline. And that is really important because lots of the tiny sea creatures in the ocean build hard shells, and lots of them build hard shells out of calcium. So calcium carbonate, for example. And to make calcium carbonate, you need a slightly alkaline environment. So, a mussel or something we can pick up and wave around, but actually most of the life in the ocean is too small for us to see. And so the little sun harvesters, the equivalents of plants and trees on land, are single cells, but they have little calcium shells. It depends quite a lot on which creature it is. But in principle, if you make the ocean less alkaline, you push it down towards the acidic end, energetically it makes it harder for a lot of those things to build their shells. And they really need their shells. And they're right at the base, the bottom of the food chain. They feed everything else in the ocean. There are some species that do a bit better and some that do a bit worse. Actually, the pH, the alkalinity or acidity of the ocean, does vary quite a lot from place to place anyway. So it's global averages where it's changed, but none of it looks good. If you're changing the chemistry, you're potentially changing how easy it is for things to grow. And that then could have an impact on other ecosystems.
I mean, you mentioned the blue marble photo, right? We talked about it earlier as well as one of those moments where we really realised this is a blue planet, right? And, you know, we were talking about it before. I think so much of how you view the ocean, how you value the ocean, is dependent on whether you have access to it, how you view our planet. And that is very different depending on where you are culturally, you know, how you were brought up.
Yeah, so one of the interesting things, and it's quite an obvious difference, but it's also very clear, is that countries in places where there are big storms tend to see the ocean as a violent monster that's coming to get them. And places where the ocean is warmer and a bit friendlier to humans tend to see it as a colleague, a companion, rather than that thing over there that's going to kill us. So, for example, the Pacific Islanders, Polynesia is and has been the greatest ocean civilization on Earth. They regularly navigated between tiny islands across a gigantic ocean. And they knew how to do it. It's not chance. They were skillful enough to use the signals of nature to navigate these enormous distances. But what that meant is that the ocean was the thing that connected these islands, not something that separated them. But they tended not to get massive, great big storms. Whereas here in Northern Europe, you know, the west coast of Ireland is slammed by big storms quite regularly. So, you know, you're not going out in that unless you have to. So even culturally, as you say, people have very different attitudes to it. But actually, our popular culture sets our attitudes to all sorts of things that we can't go and see. I mean, people watch films about aliens and about, I don't know, life on other planets and about Antarctica. These are not places people go to, but they have a relationship with them which is mediated by what they hear. We now have the advantage that we have amazing imagery from all sorts of places. We have satellite images of the ocean. We have underwater images of the ocean. We can read about it, you know, we can find things on YouTube or wherever. So we actually have a much larger selection of views of the ocean to pick from. However, they are still very biased to the ocean either being a violent obstacle or to it being a coral reef. And the honest answer is it's much more interesting than either of those things. And so I still think we have a very simple view of the ocean. And really, what we need is to understand that the ocean is a complex place. It does big things, it does small things, it does fast things, it does slow things. It has all kinds of different environments inside it. It's got the equivalents of deserts and rainforests. It's complex. It's not just a big pond. And I think that's the thing that we're not quite getting across in all of these the ways now that are what we hear about the ocean is mediated. They're very cliched. When people say this terrible thing which is not true, which is that we know more about the moon than we do about the deep ocean, categorically not true. Not true.
I've had that a lot.
Complete nonsense, right? It's nonsense, and it's damaging nonsense. You can tell I care quite a lot about this.
Yeah.
And so it's nonsense because of course we know more about the ocean than we know about the moon. 12 men went to the moon in the late 1960s and early 1970s with very primitive equipment, and they brought back some rocks. And that's what we know about the moon, along with a lot of imaging. Thousands of people like me have been to sea, we've studied it, we've sent submersibles down to the deep ocean, we have mapped it, we've got chemistry, it's moving. The thing is, the ocean is a much richer environment, it's much more interesting. And every time people say, oh, well, we know more about the moon than we do about the deep ocean, they make the deep ocean sound like the moon. They make it sound like a dead, barren rock. And it isn't. And yes, there's loads and loads and loads of things we don't know about it. But there's so much that we do know. And of course, there are many great scientific adventures still to have, finding out all the things about the ocean that we don't know. But to say that we know more about the moon than we do about the deep sea is wrong, and it's damaging, and it's an insult.
Well, your book is all about appreciating the machine, everything it does for us, looking at it rather than the green planet as a blue planet. How would you improve the ocean's PR?
So I think we just need more and richer ocean stories. But talking about the water is really important. When we think we're talking about the ocean, we're almost always talking about things in it: fish, whales, pollution, ships, whatever. Perfectly valid. But that's not the whole story. The water, how it's moving, this dynamic engine, that is the story to start from. Everything else is just swimming around on its insides. And so if you turn your view of the ocean, if you start with the water and move outwards, you've got a frame to hang all of that richness on. And I think that's how you get started.
Helen, thank you so much for coming in and speaking to us.
Yeah, really appreciate it.
Thanks for having me on.
And thank you so much for watching. And don't forget, you can subscribe to the BBC World Service YouTube channel so you don't miss a thing.
And if you have a climate question of your own, do comment it below and we'll try and answer it in a future show. I'm Greg Jackson.
I'm Jordan Dunbar, and we'll see you next time.